Good day, and welcome to our chemistry class. And in chemistry today, we shall be looking at the topic solubility. Now, when we hear solubility, what comes to mind is solution. And we have a solvent which dissolves in solute to produce the solution. A solution is any homogeneous mixture which is formed when a solvent dissolves one or more solutes, while the solvent is the substance which dissolves the solute. We have a popular universal solvent, which is water. Other solvents include acetone, ethanol, etc. And a solute is a substance that dissolves in another substance. And take note that a solute can be solid or liquid or gas. When a solution is formed, it is possible that it will be homogeneous or heterogeneous. A homogeneous solution is a one-phase solution in which the solute dissolves uniformly. For instance, salt, that is NaCl, which is dissolved in water, will produce a homogeneous solution, whereas an heterogeneous solution contains one or more than one phase and does not produce a uniform solution. An example is a mixture of oil and water. No matter how you try to mix it, you will end up having two phases, whereby the water, which is denser, will go down, while the oil, which is less dense, will be on top. Now, solute, which we said is the substance which dissolves in a solvent, could be a solid, it could be a gas, it could be a liquid. So let's take note that solute does not always necessarily have to be a solid. A solid such as a solid such as NaCl is a solute. Hydrochloric acid in a liquid form can also stand as a solute, and carbon dioxide can also stand as a solute. And don't forget that carbon dioxide is a gas. There's a limit to which a solute can dissolve in solvent. At first, when it is dissolved in solvent, it tends to dissolve completely and it forms an unsaturated solution. So at this temperature, we will say that an unsaturated solution is that solution which can dissolve more of the solute. If more solute is added, we would end up having a saturated solution. A saturated solution is one which contains as much solute as it can dissolve at that particular temperature in the presence of undissolved solute. So what we are saying now is that a saturated solution contains as much solute as it can contain. An addition of more solutes into the solution would make it become supersaturated. And so a supersaturated solution is defined as that solution which contains more solute than is required at that particular temperature. And so some point of emphasis here are the solutes, the solvents, and temperature. Because when we tamper with the temperature, it is possible that more solute will dissolve or more solute will precipitate or crystallize. Now, when we talk about solubility of a solute in a solvent at a particular temperature is the number of grams of the solute that is required to saturate 100 grams of the solvent. So in solubility, we are saying that a solute is dissolved in 100 grams of the solvent. Hence, 100 grams is mostly the reference point, or it's also defined as the number of moles of solute required to saturate 1 dm cubed of the solvent. Hence, we have another standard which is 1 dm cubed of the solvent. So where we have 1 mole of the solute in 1 dm cubed of the solvent. And it is important to note that Solubility of solids mostly increases as temperature increases, except for certain solids such as calcium hydroxide, calcium tetraoxosulfate 6, whose solubility decreases as temperature increases, and also that pressure has no effect on solubility of solids at all. Likewise, the solubility of gases decreases as temperature increases. And lastly, that increase in pressure increases the solubilities of gases. So as pressure has no effect on the solubility of solids, pressure has effect on the solubility of gas. Now, let's deal with questions on solubility. Question 1. At 25 degrees Celsius, 23 grams of potassium chloride dissolved in 100 cm cubed of water to give a saturated solution. What is the solubility of these salts in A. grams per dm cubed of the solvent at this temperature, B. moles per dm cubed? Now from this question, we're told that at 25 degrees Celsius, 23 grams of chlorine dissolved in 100 cm cubed of water. And so from here we have that 100 cm cubed of solvent was saturated by 23 grams of potassium chloride. What if we have 1000 cm cubed? And don't forget that 1000 cm cubed equal to 1 dm cubed. And so if you have 1000 cm cubed of the solvents, how many grams of KCl are we going to have there? So we cross multiply. So 23 multiplies 1000 and 100 multiplies x, which is 100x. So x equal to 23 times 1000 divided by 100. So we have 230 grams of potassium chloride. The B part of the question says that what is the solubility of this salt in moles per dm cubed? When we have a mole per dm cubed, which is a molar concentration, we should take note that the concentration in mole per dm cubed is equal to concentration in gram per dm cubed divided by the molar mass of the salt we are talking about here, which is potassium chloride. So first we will look for the molar mass of potassium chloride. We are given potassium to have an atomic mass of 39 and chlorine to be 35.5. And so when we add this, it gives 74.5 grams per mole. Hence, the concentration in mole per dm cubed equal to the concentration in gram per dm cubed, which is this. This is 230 grams in 1 dm cubed. So we have 230 over molar mass, which is 74.5. When we divide this, it produces 3.09 mole per dm cubed. So that is the concentration. Here is the next question, which says 30 grams of sodium chloride saturates 15 grams of water at 10 degrees Celsius. Calculate the solubility of sodium chloride at that temperature in grams per 100 grams of solvent. Now in this question, we were told that 30 grams of sodium chloride saturates 15 grams of water. So we have that 15 grams of water, which is the solvent, was saturated by 30 grams of NaCl. Now at this particular temperature, how many grams of sodium chloride will saturate 100 grams of the solvent? So 100 grams of the solvent, which is water, will be saturated by how many grams of NaCl? And so we'll cross multiply, that is 15 multiplied by x equal to 100 times 30. So x equal to 100 times 30 divided by 15. and that is 200 grams of sodium chloride, which is per 100 gram of a solvent. Here's the next question, which says an evaporating dish weighed 31.18 gram when filled with a saturated solution of copper 2 tetraisosulfate 6 solution at 32 degrees Celsius. It weighed 48.39 grams. After evaporation to dryness, the evaporating dish and residue weighed 33.98 gram. Calculate the solubility of copper 2 tetraisosulfate 6 crystal solid at 32 degrees Celsius in grams per 100 gram of solvent. So here is how we state our values, and this is done at the temperature 32 degrees Celsius. Okay, so in the question we're told that the evaporating dish weighed 31.18 gram, but when it was filled with CuSO4 solution, it weighed this, that is 48.39. Then after evaporation to dryness, the evaporating dish and the residue was 33.98, which is this. So first is that the mass of dish plus CuSO4, that's the dry CuSO4, is 33.98 gram. And for the dish, we're given to be 31.18 gram. So for us to get the mass of the CuSO4 alone, we will subtract 31.18 from 33.98, and that gives 2.80 gram as the mass of the solid copper 2 tetraisosulfate 6. Next, when the copper solution, that is the copper solid with its solvent, were poured into the dish, it weighed 48.39 gram. And when it was evaporated, this is what we have. Hence, the mass of the solvent which was poured will be 48.39 minus 33.98, and that will give 14.41 gram. This means that 14.41 gram of solvent was saturated by 2.80 gram of CuSO4. That is what this insinuates. And if this is the case, we're told to find the mass of the solid which will saturate 100 gram of the solvent. So if you have 100 gram of the solvent, what is the mass of CuSO4 that will be capable of saturating it? So what we'll do is we'll cross multiply. That is 100 multiplies 2.80, then 14.41 multiplies x. We make x the subject, and we have 100 times 2.80 divided by 14.41. And when we calculate this, we'll have 19.43 gram of copper 2 tetraisosulfate 6 per 100 gram of the solvent. Here's the next question, which says at 15 degrees Celsius, the solubility of sodium chloride is 42 gram per 100 gram of solvent. Calculate the mass of sodium chloride in 10 gram of a saturated solution at the same temperature. Now, when we take a look at this question, we have that 42 gram of sodium chloride in 100 gram. Hence, mass of the solution equal to the 42 gram of the salt plus the 100 gram of the solvent, and that gives 142 gram. So this is the mass of the solution. So from here we have that 142 gram of the saturated solution, it contains 42 gram of sodium chloride. If you have 10 gram of the saturated solution at that same temperature, what is the mass of sodium chloride it will contain? So we have 10 gram of the saturated solution will contain how many grams of sodium chloride? And so we cross multiply, that is x multiplies 142 equal to 10 times 42. So we have x equal to 10 multiplied by 42 over 142. And that gives 2.96 gram of sodium chloride in 10 grams of desaturated solution. Here's the next question. It says the solubility of copper 2 tetrahydrosulfate 6 at 100 degrees Celsius is 50 gram in 100 gram of water, and at 20 degrees Celsius is 5 gram. If 120 gram of saturated solution at 100 degrees Celsius is cooled to 20 degrees Celsius, calculate the mass of copper 2 tetrahydrosulfate 6 crystal which will be deposited. Now in this question, at 100 degrees Celsius, we add 50 gram in 100 gram of water, and at 20 degrees Celsius, we have 5 gram in the same 100 gram of water, meaning that as the temperature reduced, less salt was found there. Let us first get this written down. So at 100 degrees Celsius, the mass of the saturated solution, equal to the mass of the salt in it plus the mass of the solvent, which is 50 plus 100, and that gives 150 gram. Then at 20 degrees Celsius, the mass of the saturated solution of copper 2 tetrahydrosulfate 6 equal to the mass of the salt inside it plus the mass of the solvent, which is 5 plus 100. So we have 105 gram. This means that when you cool from 100 degrees Celsius to 20 degrees Celsius, there will be a particular mass that will be precipitated. So when cooled from 100 degrees Celsius to 20 degrees Celsius, the mass of salt that precipitated out was 150 gram minus 105 gram, and that gives us 45 gram. Now this question says that if we have 120 gram of saturated solution at 100 degrees Celsius, which is cooled to 20 degrees Celsius, we should calculate the mass of copper 2 tetrahydrosulfate 6 that we deposited. Hence, in this case now we have 150 gram initially of saturated solution. When it was cooled from 100 to 20, we had 45 gram which precipitated out, or which was deposited. Hence, when we have 120 gram of this same copper 2 tetrahydrosulfate 6, what will be the mass of CuSO4 that will precipitate out? So we have it as x. And so what we have is that x multiplies 150, and then 45 multiplies 120. So x equal to 45 multiplied by 120 divided by 150, and that will give 36 gram of CuSO4. That's the answer. Next question says the solubility of silver chloride at 50 degrees Celsius is 10.24 gram per 100 gram of solvent, and at 10 degrees Celsius it is 2.15 gram. Calculate the mass of silver chloride precipitated when a saturated solution of 50 gram of silver chloride was cooled from 50 degrees Celsius to 10 degrees Celsius. So what we do is that we're told that at 50 degrees Celsius we had 10.24 gram per 100 gram of the solvent. Hence, mass of silver chloride solution will be equal to mass of the salt, which is 10.24 gram, plus mass of the solvent, that's 100, and this produces 110.24 gram. Next, at 10 degrees Celsius, mass of silver chloride solution equal to the mass of the salt, which is 2.15 gram, plus mass of the solvent, and that is 102.15 gram. Now, on cooling from 50 degrees Celsius to 10 degrees Celsius, what is the mass of silver chloride that precipitated? So we have that precipitated mass from 50 to 20 degrees Celsius will be 110.24 minus 102.15, and that will give 8.09 gram of silver chloride. Next, we have to calculate the silver chloride precipitated when we have a solution of 50 gram which was cooled. Now, when we had a mass of silver chloride solution which is 110.24 gram, which was cooled from 50 to 10 degrees Celsius, we had 8.09 gram deposited. But if we have a solution of 50 gram of the same sodium chloride, what will be the mass of silver chloride that will be precipitated? So we cross multiply, that is x multiplies 110 equal to 8.09 times 50. And so x equal to 8.09 times 50 divided by 110.24. And that gives 3.67 gram of silver chloride. Hence, that is the answer. We have the next question here, which says that the solubility of sodium chloride at 100 degrees Celsius is 39.8 gram, and at 15 degrees Celsius it is 35.9 gram. If a saturated solution of sodium chloride made in 80 gram of water at 100 degrees Celsius is cooled to 15 degrees Celsius, calculate the mass of sodium chloride which will be precipitated. Now, for this question, we have that at 100 degrees Celsius, 39.8 gram was in 100 gram of solvent to precipitate it. If we have a saturated solution of sodium chloride, which is at 80 gram of salt, at that same 100 degrees Celsius, all right? So what we need to do first is this. At 100 degrees Celsius, we have 100 gram of water, which dissolves 39.8 gram of sodium chloride. So if we now have 80 gram of water, what will be the mass of salt that will precipitate it? So we have that x equal to, so we cross multiply as x multiplies 100. So we have 80 multiplied by 39.8 divided by 100 gram, and that will give 31.84 gram of sodium chloride. So that's the first part. Now we now have that, and at 15 degrees Celsius, 35.9 gram is what precipitated 100 gram. We have it there that at 15 degrees Celsius, 100 gram of water dissolved 35.9 gram of NaCl. That's 100 gram. These are the standard. But in this case now, we do not have 100 gram. We have 80 gram of water. So if we have 80 gram of water, we have 31.84 gram. If this water of 80 gram was cooled to 15 degrees Celsius, what will be the mass of silver chloride we have? So we have 80 gram of water. What is the mass of salt that will dissolve into it to have a saturated solution? So we have x. So x here equal to 80 times 35.9 divided by 100. And that produces 28.72 gram of sodium chloride. We have to calculate the mass of sodium chloride which will be precipitated. That is, when you reduce the temperature from 100 degrees Celsius to 15 degrees Celsius when you have 80 gram of water. So we have that mass of chloride which will precipitate out will be 31.84 gram minus 28.72 gram, and that will give 3.12 gram of chloride. We are solving this based on 80 gram of water. All right, so here we want to look at plotting a graph showing solubility of salt. Here we have the graph and the solubility on the y-axis in gram per 100 gram of water, and on the x-axis we have our temperature in degrees Celsius. And here is a table which we are to plot on this graph. So first is that at 0 degrees Celsius of temperature, we have 28 grams in 100 gram of water. So we'll go ahead and have an estimate over here. So what we can get basically from this table on the board is an estimate. At 10 degrees Celsius, we have 31. So 31 will be somewhere around here. That's at 10. Then at 20 degrees Celsius, we have 34. So we have 34 somewhere close to this place. At 30 degrees Celsius, we have 37. So we have 37 very close. Then at 40 degrees Celsius, we have 40. So we have 40 somewhere around here. And at 50 degrees Celsius, we have 43. So here is 50, we have 43. Then we will join this. Now from this graph, we could be told to find the solubility of the salt at particular temperature. And all I'm going to do is to give you an estimate of how it could be done. So for instance, if we are asked to find the solubility of the salt at 50 degrees Celsius, all we need to do is we'll trace it up and then we'll trace it towards the left to get where it is. So if you are using a proper graph, you will get the right answer. So that's how you get the solubility of the salt at a particular temperature. Likewise, you could be asked that at what temperature would you have a mass of, let's say, 35. So if you have at mass 35, you have 35 over here. So you choose your 35 here and then you trace it to the right and then you move down. That's how you get your mass at 35. At times, you could be told that you should find the mass of a particular salt which you precipitate when the solution is cooled from one temperature to the other. So for instance, let's say that when this particular solution was cooled from 50 to 20, what will be the mass that we precipitated? So what you do is that, let's say that at that 50 degrees Celsius, you trace it up and then you get your mass. You record the mass that at 50 degrees Celsius, you got a particular mass. Let's say we have 43 gram in 100 gram of water. Okay, so let's say at 20 degrees Celsius, so we'll trace it up and then to the left. And when we trace it to the left, we'll find out, okay, at 20 degrees Celsius, we got a mass of 34. So I'll be that at 20 degrees Celsius, we have a mass of 34 gram per 100 gram of the solvent. Hence, the mass of salt that precipitated out will be 43 gram minus 34 gram, and that will give 9 grams of the salt. And so that is what the solubility curve or graph is about. Next question. In an experiment to determine the solubility of sodium chloride at 30 degrees Celsius, it was observed that 54.50 gram of the saturated solution of sodium chloride contain 24.50 gram of sodium chloride solid. A. Calculate the solubility of sodium chloride at 30 degrees Celsius. And B. If the solubility at 90 degrees Celsius is 240 gram per 100 gram of solvent, what mass of sodium chloride will be deposited when 120 gram of the saturated solution at 90 degrees Celsius is cooled to 30 degrees Celsius? Alright, so in this question, we're told that at 30 degrees Celsius, 84.50 gram of a saturated solution contains 24.50 gram of sodium chloride. So from here, what is the mass of the solvent? So we first find mass of solvent will be mass of the saturated solution minus the mass of the salt. So we have 54.50 gram minus 24.50 gram, and that will give 30 gram of solvent. 30 gram of water dissolves or saturated 24.50 gram of sodium chloride. What will be the solubility of the sodium at that same temperature? Meaning that if you have 100 gram of water, what will be the mass of sodium chloride, which will saturate it in order to determine the solubility? So we have x multiplies 30. So we have x equal to 24.50 multiplied by 100 divided by 30. And this will give 81.70 gram of the salt at 100 gram of the solvent. Now, B says if the solubility at 90 degrees Celsius is 240 gram per 100 gram of solvent, what mass of sodium will be deposited? So we have here that at 90 degrees Celsius, so meaning this salt is highly soluble. So at 90 degrees Celsius, we will have that mass of the saturated solution is equal to the mass of the salt plus the mass of the solvent, which is 240 plus 100 gram, and that gives 340 gram of NaCl solution. Now, what mass of the sodium chloride will be deposited when 120 gram of this saturated solution at 90 degrees Celsius is cooled? Now we have that 340 gram of sodium chloride solution, which is saturated at 90 degrees Celsius, and at 30 degrees Celsius we have 81.70 gram. We have 81.70 gram of sodium chloride at 100 gram. So for this one, we have that the mass of the saturated solution here is the mass of the salt plus the mass of water, and that gives 181.70 gram. So we state here that at 90 degrees Celsius we had 340 gram of saturated solution, and at 30 degrees Celsius we had 181.70 gram of the saturated solution of the same salt. So when we cool it from 90 to 30 degrees Celsius, what is the mass that precipitated out? So we have it at 340 minus 181.70, and that will give 158.3 gram of the salt. So if we have 120 gram of the saturated solution at 90 degrees Celsius, what is the mass that will be precipitated out if it is cooled to 30 degrees Celsius? Now we have that when we had 340 gram of the salt at 90 degrees Celsius, and which was cooled to 30 degrees Celsius, 158.3 gram of salt is what's precipitated out. Now if you have 120 gram of the saturated solution, this is saturated solution, so let's have it there as saturated. So if you have 120 gram of saturated solution of sodium chloride, what is the mass of salt that will precipitate out when cooled from 90 to 30? And so we have 340 multiplied by x equal to 120 multiplied by 158.3. Hence, x equal to 120 times 158.3 divided by 340. And that will give 55.87 gram of sodium chloride. So in summary, 158.3 gram of sodium chloride was deposited when cooled from 90 to 30 degrees Celsius. Then when this particular salt of this concentration was cooled from 90 to 30 degrees Celsius, this is the mass of sodium chloride which was deposited. Alright, so here's the next question. It says the solubility of copper 2 tetraoxosulfate 6 at 50 degrees Celsius is 120 gram per 100 gram of solvent, and at 15 degrees Celsius is 30 gram per 100 gram of solvent. What mass of copper 2 tetraoxosulfate 6 solution must be taken to produce 30 gram of copper 2 tetraoxosulfate 6 crystal when saturated solution at 50 degrees Celsius is cooled to 15 degrees Celsius? Alright, so for this question, we have that at 50 degrees Celsius, the mass of saturated solution of copper 2 tetrasulfate 6 is equal to the mass of the solute plus the mass of the solvent that dissolved it, and that gives 120 gram plus 100, and that is 220 gram. Then at 15 degrees Celsius, mass of saturated solution, the mass of what was gotten was 30 gram in 100, so that will be 30 plus 100, and that gives 130 grams. The mass of CuSO4 crystal that was deposited when it was cooled from 50 to 15, and that will be 220 minus 130 gram, and that will give 90 grams. So this is the mass of CuSO4 crystal which crystallized out. Now we're asked to find the mass of solution that will produce 30 grams when it is cooled from 50 degrees Celsius to 15 degrees Celsius. From here, we have that 90 gram of CuSO4 crystal was deposited when 220 gram of the saturated solution was cooled from 50 to 15. So if we have 30 gram of CuSO4, what is the mass of saturated solution we must have had? So we are looking for X of saturated solution. And so we have that X equal to 30 multiplied by 220 divided by 90. That leaves us with 73.33 gram of CuSO4 solution. So that is the answer. Next, we want to look at solubility and solubility products, still under the topic solubility. Now we have a reversible equation, such as if CD is decomposed into C and D. Taking C as a solid, and here we have aqueous of C and aqueous of D. We can determine the solubility product by having that the solubility constant is equal to the concentration of C, which is plus, and here is minus, multiplied by the concentration of D over the concentration of C and D. Where this is solid, here we have aqueous and this is aqueous. Now under solubility, the concentration of solid is equal to 1. So this is equal to 1. When this moves here, we have, just like cross multiplying, we'll have Kc to bracket Cd, which is the concentration of the reactant, equal to the concentration of C and the concentration of D, and that is equal to Ksp, where Ksp is known as solubility product constant. So this is the solubility product constant. Several salts have their own solubility products. Most of them at 25 degrees Celsius. So these are constants. So solubility product is a measure of solubility. And the greater the solubility of an ionic solid, the larger will be the value of its solubility product. We are going to solve some questions under solubility product. The question says that we should write down the solubility product expression for a saturated solution of the following substances in water. Roman figure 1, silver bromide, Roman figure 2, magnesium hydroxide. Roman figure 3, calcium fluoride. Now let's take the first one, silver bromide, which is a solid. When it is dissolved in water, it produces Ag plus bromide minus. Here we have a solid and we have aqueous because they are in solution, and we have aqueous over here, meaning that the solubility product constant is equal to the concentration of silver multiplied by the concentration of bromine over the concentration of the two of them, that is the solid. Now here we have solid, we have aqueous over here, and we have aqueous over here. Hence, the solubility product constant, since this is equal to 1, the solubility product constant is equal to Ag plus aqueous multiplied by bromine minus aqueous. This is the answer. We want to write the solubility product expression for magnesium hydroxide. Magnesium hydroxide. We have two over here. Magnesium hydroxide, which was dissolved in water to produce Mg2 plus OH minus. To balance this equation, we know we have a 2 over here, and so we have 2 here. Now this 2 plus here is the oxidation number of magnesium, while the minus over here is the oxidation number of hydroxyl, that is OH. So from here, this is a solid, this is aqueous water, and this is aqueous. Now we have that the solubility product constant equal to the concentration of magnesium multiplied by the concentration of hydroxyl ion. Now take note that we have 2 over here as the 2 moles, so we have it raised to power 2 over the concentration of magnesium hydroxide. Now these are aqueous because they are in water. Then here we have a solid. Now we have that the concentration of a solid is 1. So with that, we will now have that the solubility product constant of magnesium hydroxide equal to Mg, concentration of magnesium ion, multiplied by concentration of hydroxyl ion raised to power 2, and then we have aqueous. We have aqueous of this, and we have aqueous of this. So that is the answer. And then lastly, for calcium fluoride. Calcium fluoride. Here we have calcium fluoride, which dissolves in water or in a solvent to form calcium 2 plus fluorine minus. This 2 plus is the oxidation number of calcium, while this minus is the oxidation number, that's -1. That's the oxidation number of fluorine. Now we have this in solid, we have calcium in aqueous form, we have fluorine in aqueous form. And we need to balance this equation because we have 2 atoms of fluorine here and we have just 1 atom here. And so we have, if we put 2 here, that has balanced the equation. Next is this, to find the solubility product constant, which is equal to calcium concentration multiplied by fluorine concentration raised to power 2 divided by concentration of calcium fluoride solid. So we have solid, we have aqueous, and we have aqueous over here. Now with this information, since we know that the concentration of a solid is 1, and so this will be out, and then we have Ksp equal to calcium concentration multiplied by fluorine concentration. Question says the solubility of silver chloride in water at 298 Kelvin is 1.65 times 10 to the power of -5 mole per dm cubed. Calculate the solubility product constant of silver chloride at this temperature. Silver chloride dissolves in water to form silver ion plus chlorine ion. Solid for silver chloride, and we have aqueous here and aqueous over here. Now, from what we have on the board, this is already balanced. And so we have that 1 mole of silver chloride produces 1 mole of silver ion and 1 mole of chlorine ion. In the question, we're told that the solubility of silver chloride is 1.65 times 10 raised to the power minus 5 mole per dm cubed. We are saying that the solubility of this silver chloride is 1.65 times 10 to the power of minus 5 mole per dm cubed. That is, this is number of moles in 1 dm cube. So how many moles of silver chloride are we going to have in 1 dm cube? How many moles of chlorine ion are we going to have? It's going to be the same, since 1 mole of silver chloride is 1 mole of silver ion and it's also 1 mole of chlorine ion. And so we have 1.65 times 10 to the power minus 5 for silver ion, and we have 1.65 times 10 to the power minus 5 for chlorine ion. Next, we have that the solubility product constant of silver chloride equal to the concentration of silver ion multiplied by the concentration of chlorine ion divided by the concentration of silver chloride. Here we have solid, we have liquid, we have aqueous over here. The solubility of silver chloride equal to 1. And so with that, we will have that the KSP equal to silver ion concentration multiplied by chlorine ion concentration. Since 1 mole of silver chloride equal to this, we have to find the solubility product. So the product of this and this. For what we have here, we have 1.65 times 10 to the power minus 5 for silver. So we will have that. So that is the solubility. That's 1.65 times 10 to the power of minus 5. Multiplied by that of chlorine, that is the solubility of chlorine, which is 1.65 times 10 to the power of minus 5. When we multiply this out, it gives 2.8 times 10 to the power of minus 10 mole raised to power 2, and then we have the per dm raised to power 6. Now it is mole squared because we have mole per dm cubed here and we have mole per dm cubed here. So if mole multiplies mole, we have mole squared. And if dm raised to power 3 multiplies dm raised to power 3, to become dm raised to power 6. This is a question of indices. Hence, this is the solubility product constant of silver chloride. Next question says the solubility of calcium fluoride in water at 298 Kelvin is 2.2 times 10 to the power of minus 4 mole per dm cubed. Calculate the solubility product constant of calcium fluoride at this temperature. So we have calcium fluoride, which dissolves in water to form Ca2 plus fluorine minus. And here we have a solid, we have aqueous, and we have aqueous. We need to balance this equation. We have 2 atoms of fluorine here, but we have 1 over here. So we have 2, which we place here. So the difference in this particular question is how do we calculate the solubility product constant when we have 2 moles. This means that 1 mole of calcium fluoride will yield 1 mole of calcium ion and 2 moles of fluorine ion. Hence, if we have the solubility of calcium fluoride to be 2.2 times 10 to the power minus 4 mole per dm cubed. Since 1 mole is 1 mole here, so it will be 2.2 times 10 to the power minus 4 over here. But for fluorine, it will be different because they have 2 moles, so we'll multiply it by 2. So 2 times 2.2 times 10 to the power minus 4. And that gives 4.4 times 10 to the power minus 4. Next, we proceed. So we have that the solubility product constant will be equal to concentration of calcium ion multiplied by concentration of fluorine ion divided by concentration of calcium fluoride, which is solid. So we have aqueous here and we have aqueous over here. Since we know that the concentration of a solid equal to 1, so we'll be left with this. And so we'll have that calcium ion is 2.2. So we have 2.2 times 10 to the power of minus 4 multiplied by, so for fluorine we need to place 2 over here because 2 moles of fluorine, so we place 2 over here on top there. So take note of that. The solubility of the fluorine ion, which was given here, is 4.4. So we have 4.4 times 10 to the power of minus 4 raised to power 2, and so we have our 2 on top. And so when we multiply all this out, that is 2.4 multiplied by all this, we will end up having 4.3 times 10 to the power of minus 11 mole raised to power 3 and dm raised to power 9. This is the solubility product constant of calcium fluoride. Now you'll be wondering, why do we have 3 here and we have 9 here? We have 3 there because here, this is the first one, because this one is mole per dm cubed. This other one is mole per dm cubed, but we have raised power 2 of this. So with this we have mole per dm cubed multiplied by, this is mole per dm cubed again, so mole per dm cubed, then it's raised power 2 multiplied by mole per dm cubed. So mole times mole gives 3 moles, 3 of this, then dm cubed, that's 3 plus 3 plus 3, and that gives 9. So that's how we arrive at the final answer. Next question says, calculate the solubility of magnesium hydroxide in water at 298 Kelvin. Given that the solubility product constant of magnesium hydroxide at 298 Kelvin is 1.8 times 10 to the power of minus 12 mole raised per 3 per dm raised per 9. Now we have magnesium hydroxide. We have to calculate the solubility. So magnesium hydroxide, it dissolves in water to form magnesium plus OH minus. Now the magnesium here has a valency of 2 plus, and here we have a solid and we have aqueous and we have aqueous. Now if you want to understand all this oxidation number, you need to check our class on redox reaction or generally on redox. Now from here, this equation is not balanced. We have 2 atoms of hydroxyl here, so we place 2 over here to have it balanced and equal. Now what we are after here, we are given the solubility product constants, but we have to find the solubility of magnesium hydroxide itself in water. So from here we have that 1 mole of magnesium hydroxide produces 1 mole of magnesium ion and then 2 moles of hydroxyl ion. Then the solubility product constant equal to the concentration of magnesium ion multiplied by the concentration of hydroxyl ion, which is raised power 2, divided by the concentration of magnesium hydroxide. Now this is a solid, aqueous. Since we have here that the concentration of magnesium hydroxide is 1, so we'll take this out, and so we'll be left with solubility product constant is equal to Mg2 plus then OH minus 2. We're given the solubility product constant as 1.8 times 10 to the power minus 12. So we have 1.8 times 10 to the power minus 12. That is what we're given as the KSP of magnesium hydroxide. We will now say that 1.8 times 10 to the raised power minus 12 equal to, let us represent all this with a variable, let's say y, and then let's represent this also with a variable, just that it will be squared, which is also y, since they will be the same thing, just that this one is squared. Now this means y times y squared, that gives y raised to the power 3 equal to 1.8 times 10 raised to the power what? Minus 12. Under rules of indices, this raised to the power 3 comes over here and becomes cube root of 1.8 times 10 raised to the power minus 12 equal to y. So the cube root of this will be equal to 1.2 times 10 to the power of minus 4 mole per dm cubed. So from here, we have that the solubility of magnesium hydroxide in water equal to 1.2 times 10 raised to the power minus 4. Likewise, for magnesium ion is also equal to this. But for hydroxyl ion, which is multiplied by 2, will be 2 times 1.2 times 10 raised to the power minus 4. And so we will have 2.4 times 10 to the power of minus 4 mole per dm cubed. So this will be the solubility of the OH minus.